Good afternoon or good morning in whatever time zone you are. I'm Jean-Louis Van Bellen. I've done a few videos and papers on YouTube and on ResearchGate. I'm not a professional academist. I got a lot of positive reactions, but also some negative ones. The negative ones are mainly, who are you? What are your credentials? I'll be open on that. My credentials are open research. I don't have a PhD in physics, but I've done a lot of other stuff. And basically, about 2 years ago, I looked at these things. I've been looking at these things all of my life, quantum physics, what is it? And I sort of suddenly had this idea that, if the matter wave frequency, if you would interpret that as an orbital frequency rather than a linear one, then everything comes out of it. You've got a model for matter particles, you've got a model for light particles. You start thinking about how they interact, and a lot of what I would call mysteries sort of disappear. There's no spooky action at a distance. You can explain everything in terms of conservation laws, conservation of energy, of linear and angular momentum, and a lot of other things. So I will be short because this actually concludes my, I would say, my publications of what I found. So I've been working on this for 10 years. I tried to get some publishers interested. That didn't work. And then I haven't invested much in terms of trying to sell my ideas to the regular channel, and I decided to put some papers on ResearchGate, which I find excellent. So that has gone rather well. I started publishing in 2020, and I'm still scoring quite well. My ResearchGate score is higher than 99% of ResearchGate members who first started publishing in 2020. As a result of that, I shot up with a score that is now higher than 80% of ResearchGate members, and that includes a lot of PhD students and professors. And in the field specifically of quantum physics, a research interest score is higher than 76%, and it's still going up. So I don't try to sell myself here. I think a lot of people struggle with these questions and try to understand. And so I'm continuing a bit like, what Boltzmann said: if you think you've found something, then bring it forward. Bring forward what is true and write it out so that it's clear. On the last line, defend it to your last breath. I'm not going to do that. I'm not a mad scientist, who thinks that he's got the last say on these things. Not at all. So this is a concluding thing where I'm gonna basically, I thought let me conclude by making the shortest video or presentation ever on quantum physics, the shortest introduction to quantum physics ever. It's hidden by the camera view, I see. But I could also call it like the end of physics, because that's what it is. There's no mystery. We know what matter is. An oscillation of charge, basically, as I'll explain in a moment. And then I will very quickly go over the main findings and the key equations, because that's what people want to hear. What is the equation of physics, or the equation of life? There's not one, but there are a few, and they are related, and you could put them in one equation, sort of this monster equation that Feynman said. U is 0 or W is 0, and then you can have one equation, but it doesn't explain very much. So without further ado, let's present a slide I've presented on the electron model. There's a lot of text here. I would refer to previous videos, but basically what we have is, if you think of an electron and the mass of an electron, basically you wonder, what is mass? Mass is energy. It must be energy, according to Einstein's mass-energy equivalence relationship. And so, and then you start thinking, what is a force? A force acts on something. So as far as we know, we have the electromagnetic force, and the other forces are not so clear, and I think they can be explained in terms of electromagnetic force, but that's another subject matter. But basically, yeah, you start thinking like, you know, the mass of an electron, the mass of a proton, you know, that's energy. Energy is force over a distance. The force acts on a charge. So we must have some charge inside there that is oscillating, that is moving. It is moving over a distance, and you know, because it's a particle, it stays on the same spot, it's localized. Then you think like, okay, the frequency of motion that we have there in the Broglie's matter wave, it must be an orbital motion, you know, and that's the typical interpretation of electrons, or the ring current model, as it's also called, which has been around for more than a century. I think in the beginning of the 20th century, in 1910, I think Parson came out with that. And he also thought like an electron is probably like there's a point-like charge inside, and that must be tittering around or moving around. And that's also consistent with what Schrödinger and Dirac said, like, you know, this model must be consistent because it's what we see in photon scattering experiments. You know, when we fire photons at an electron, it's not point-like, it has a radius. That's the radius that is there, 386 femtometer. Then, you know, sometimes we have elastic scattering or hard scattering. You know, the photon just bounces back without changing its energy. So, and based on that, you can see that the electron has basically, you know, two radii, actually three when it's in an atomic shell. But you know, a free electron has a sort of an interaction radius, which is, as I said, equal to that one. And then you know, inside you have a point-like charge, which is you know, that has been measured as well, which is related to that interaction radius, I would say, by the fine structure constant. And yeah, that's it basically. So mass is basically a measure of you know, the inertia of the energy of the oscillation of that point-like charge inside of the electron. And so an electron has a magnetic moment, so that reinforces that ring current model. You know, there's some point-like charge spinning around. And we also know there's an anomaly in the magnetic moment. You know, if we really have a mathematical model where that point-like charge would have zero dimension, an infinitesimally small dimension, so point-like, but zero dimension. I always say, like, you know, zero dimensional stuff doesn't exist. If it has no dimension whatsoever, then, you know, then it's nothing, right? And so this model is consistent with that. You know, the anomaly of the magnetic moment shows that this point-like charge really has, you know, it must be the classical electron radius, which is also known as the Lorentz or Thomson radius, as opposed to that Compton scattering radius. Compton was an American, so I should say not Compton, but Compton. And it's the fine structure constant alpha times a, the radius. And so yeah, but how do we get the Compton radius, the Compton radius? Very easy. You know, we have the Planck-Einstein relation. The energy is equal to Planck's quantum of action times the frequency. So it's h times f, or h bar times omega. And then I said that charge, because it's the point-like charge inside of an electron is just charge. It doesn't have any other property than charge. So it doesn't have any rest mass, no inertia to a change of its state of motion. So, you know, it must be zipping around at the speed of light inside of the electron. And so it has then an orbital velocity, and that orbital velocity, you know, if it has zero rest mass, only charge, you know, any force, any electromagnetic field, and we argue that, you know, it generates its own electromagnetic field which keeps it in orbit, that you know, must accelerate it to the speed of light. So in that sense, it's photon-like. But it's not a photon, of course, because it has charge. A photon has no charge. That's a field. You know, that's a field. What is a field? I would say that's think of a force without a charge to act upon. But so that charge, that point-like charge inside of an electron has charge, and so there is a force to act upon. I mean, that force can act upon a charge, on that point-like charge, and its velocity orbital velocity, the velocity with which it jitters around, and the electron must be the radius of the oscillation times that frequency. So that's A times omega. That's just an orbital, standard formula from circular orbitals, but it's valid here. So if we combine these two, we can say like C is A times the orbital frequency. So the frequency is A divided, well, is the inverse of the frequency is A divided by C, and that must be equal to the inverse of the frequency h bar divided by E. So from A over C equal to h bar over the energy, that's equal to h bar divided by mc square, and from that you can see that A must be equal to h bar divided by mc, the speed of light. We have it in the above the dividing line and under the dividing line, and you can calculate, and that comes out all right. So I put a lot of other comments here which you can read. I talked about that, explanations of that orbital velocity formula. The other remarks are basically, this is kind of an oscillation. If you have a thing, point-like charge moving around and around, you can analyze it in terms of, it oscillates from left to right, and it oscillates, from top to bottom and back again. Very important in this model is that it's a planar oscillation, an oscillation in one plane. Of course, the plane can move around and should move around because such a ring current has a magnetic moment. So if it moves, not in free space, but in a space that has an electromagnetic field, an electric field or a magnetic field or a combination of both, then of course, the magnetic moment will align itself to that electromagnetic field as it moves through space. And, I know the reference there, our paper on the matter wave. I should have put a hyperlink, but you'll find it on my ResearchGate page. There's a number of papers there, about almost 40 now, and almost in every paper, there's a small explanation of how that works, and in a few we explain specifically how that oscillator model works. I put a star engine of an old airplane in the up corner, because that's sort of how you could think about it. There's cylinders, forces, or a field, and they translate a linear motion into rotational motion. It's a metaphor. It is what it is, but it makes it sort of nice because the math, relativistic oscillator math, is not easy. And so if you're not very sharp in math, this metaphor might help you to understand what I'm talking about. The problem of paradox, which I struggled a lot with, is like, if this ring current model works for an electron, then it should also work to provide an explanation for the radius of a proton and its magnetic moment and other measurable properties of a proton. But when we apply that formula, we get like 0.21 femtometer. It's a lot smaller than the electron radius, and so we're missing, there have been in recent years, that's a big advance on the experimental field, very precise measurements of the proton radius, and they're even taken into account, the standard errors and systemic errors that you have, because you have different ways of measurement. The value is around that theoretical value that I have here, 0.841 femtometer. It's within the confidence intervals. It's not exactly the same, but it's within the confidence interval. So that gives a lot of faith that you say, like, that 4 times h bar, that factor 4 that we have to add to the h bar divided by mc formula, that must make sense. Feynman said that, if your theoretical model is off by a factor 2 or a factor 4 or a factor 2 times pi or whatever, some nice mathematical thing, some nice mathematical factor, then your model is probably right. And it was not only Feynman, Dirac said that, and a lot of physicists said, like Dirac, if your math is beautiful and there's just a factor difference, then something is wrong. Something is wrong with your model, but it's probably easy to correct. And so yeah, it is easy to correct. I must say that I had to think about it a little bit. But the proton, from experiments measuring the radius and interactions and all these kind of things, and it does appear to be a spherical thing, not a flat thing. In a nucleus, with neutrons, which we think are combination of positive and negative charge keeping protons together, but that's a model you will find in our papers. We think, okay, fine, if a proton has a three-dimensional structure rather than a two-dimensional structure for the electron, then that force factor must be just exactly the same one as the one that appears in the formula for the surface area of a sphere, as opposed to the surface of a circle. The surface area of a sphere is 4 times p r square. And a circle is just, p r square. So yeah, when you sort of work with spheres, three-dimensional things, often your formulas for the volume and the surface, you will have that factor 4. So I thought like we should probably reverse the logic then maybe, and say like, okay, the proton radius, it is equal to that magical and not so magical formula. A is 4 times h bar divided by mc. So then, probably what's going on is that the Planck-Einstein relation, E is h times, Planck's quantum of action times the frequency, or h bar times omega, radial frequency expressed in radians rather than in number of oscillations. Then that force factor must be there, and I sort of recently thought like, in the beginning I thought, no, we really need a geometric model, but sort of a generalized Planck-Einstein relationship. If you look at how the black body problem was solved, there's actually relations there that indeed say like, relationship energy is n times h times the frequency, with n being 1, 2, 3, 4, 5. That's valid, that is being used in these things. So the mass energy equivalence relationship, E is mc square, that's absolute, and you shouldn't tinker with that. But yeah, if you write 2 times h f or 4 times, that's not a huge theoretical problem, and you can sort of easily justify it by referring like, look at the geometry of a proton, of that it's a three-dimensional oscillation. And so then you have you work a bit around, let's say, okay, A is 4 times h bar divided by mc. We have our same charge, this is not a vector quantity. C is just the speed of light, times a radius, as said, not a vector radius, just a number, the radius times the frequency. So then A times omega must be equal to 4h divided by mc times that omega. Then you bring stuff to the other side, A times omega mc must be equal to 4 times h omega. The omega, then we use the orbital velocity formula again to say like omega is c divided by a, so the a's cancel. A times c divided by a times mc is 4 times h omega, and then you have mc square, or the energy. Mc square is the energy, is 4 times h bar divided to times omega. So that's our proton model. And then discussions now is because we have a bit of an anomaly in the proton magnetic moment as well. The reasoning should be there the same like that we had for the electron. The point-like charge is going to be much smaller, because the proton radius itself is already much smaller than the classical electron radius. So, but that point-like charge inside of a proton must be different from that point-like charge in an electron, and we can swap it around, but it sort of explains the three-dimensional structure and the fact that that positive charge inside of a proton is the point-like charge that it's jittering around is much smaller. That sort of explains why an electric positive charge and electric negative charge are two fundamentally different things, and we have the point-like charge, negative point-like charge, making up an electron, and we have a positive electric charge making up a proton. And of course we have a sort of a mirror world, the antimatter world, and I do have an explanation or a theory for dark matter, but it's complicated, not so complicated. It's got to do with the fact that the electromagnetic force as we see it in our world, in this matter world, which includes we can produce antimatter. We see antimatter being created from cosmic rays and all that. So our world, matter and antimatter, they're based on a left-handed electromagnetic force. The magnetic field vector follows the electric field vector by a phase difference of 90 degrees. So we can imagine that there in this universe maybe there's a right-handed electromagnetic force, and now we would have a, I don't know how to call them, but yeah, dark matter. It wouldn't interact with our matter because the handshake isn't there. It's got a different, I would say, space-time metric. These two forces. And so that's the theory of dark matter, but I refer to the paper on that. That's very speculative stuff. I personally believe in that. I think it's a logical explanation. I believe what Dirac said. You should really, that's how he discovered positron. If your equations tell you that there's another mathematical possibility, then probably that mathematical possibility corresponds to, a physical possibility. Why then we would have, we have more dark matter based on the patterns of how galaxies move than ordinary matter and antimatter. That's a question for cosmologists to solve. There must have been some imbalance there. I thought a bit about cosmology. There's a number of things that we can explain. We live in a universe that we can only so many billions of years ago we can see the age of the universe, but that's also the size of the universe as we know it, because we get signals or radiation from parts of the universe that are billions of years away when the universe was born. At the same time, we see it expanding, so probably there are other universes that we cannot observe outside there, and they probably tear our universe apart. That's my theory. Is the universe infinite? No, I don't believe in infinite. What's beyond then the border of the universe? Well, nothing. Nothing is nothing. So I will stop because I see that I get dragged into cosmology discussions, but I said this is a short lecture on everything, I would say. But let me move on with this model. So we have a model for an electron, a proton. We know what they are. We have a sort of a visual or a representation in our mind of what they are. We have equations that explain it. I would emphasize these are mass without mass models, like in the 60s and 70s, people were working on that. They realized, what I said, mass is basically inertia to the state of motion of what? Well, it must be charge. So you must be able to reduce mass to charge somehow, and again, the forces we have, of course we have gravity, but Einstein's general relativity theory says basically you can see that as a sort of a geometric feature of our universe, curved space, and then mass moves around in that along a geodetic trajectory. So gravity is there, yeah, but is it a force? I don't think so. It's more a geometry of a universe. So the real force we can work with and that we have to analyze is the electromagnetic force, and that works on a charge, on nothing else. A charge. What is charge? Then you will say, well, charge is charge. I'm sorry. We can't reduce it any further. There's interesting experiments where you create charge out of mega bursts of gamma rays. But that's a bit of a different discussion. Charge is charge in any case, and so there's a whole discussion: can we create charge out of nothing? And when matter and antimatter annihilate each other, it seems that charge disappears, not in any net way, because it's plus and minus charge that annihilates each other. But apart from those discussions, mass must ultimately be charge in motion. So in these two models, they explain that. They give you, I think, the most complete and maybe not very clear explanation, but it's the most complete explanation, and to me it makes a lot of sense. So we have an electron-proton model. We have, that's maybe something I want to show now. We can model that sort of ring current in an electron here. Now I go, so how does it move through space? When it's stationary, we've got that black ring, right? So the charge goes round and round, and the distance is measured here in electron volt. But that's basically because of I borrowed this from a publication. by a group of Italian physicists who allow me to use this, and I used it a lot. That black thing is sort of, yeah, you see a point-like charge moving around at the speed of light. If we sort of go to another reference frame, we think, this electron is moving, and then it's Galilean, or we should use Einsteinian relativity. But then the electron moves in relation to our place in space and in time, and we know that if we introduce here, we've got a bit of a physical explanation of relativity theory. If we introduce like a horizontal momentum or velocity, the charge also moving in a certain linear direction, then its energy, the way we measure it, will be different from the E0 I mentioned there in these equations. It will be the energy as measured because the electron as a whole has a linear velocity v, and so that comes with a non-zero momentum p. And here we do use vector. P is a vector and x is a vector. That's an axis in space, and it moves along that axis. We define our space coordinates in just the right way to say, like, our x-axis is going to be the direction in which this electron as a whole moves. So we've got that black ring, and we see that the circumference of that black ring must become smaller because the speed of light is absolute, that's not relative, and so some of the velocity must go sideways, so the ring current, the ring becomes smaller, and you see how it moves there at different electron speeds, 0.043 and 0.8 and other values. So that's where I show, like, if you have read anything about it, and I hope you have, otherwise this lecture is not useful for you. The wave function, the elementary wave function, is written as Euler's number, and the argument is plus or minus. That's the spin direction. The imaginary unit times the phase, and the phase is that delta there, and that's, I said go to the papers. It's kind of logical. That's the energy divided by h Planck. By h bar, by Planck's quantum of action, times time, and it's time in the reference frame of the electron itself. So that's why we use E0 and a t prime. So t prime, yeah. And then you can go from the energy as measured in the time as measured in the electron's own reference frame, the inertial frame of reference, to the moving frame of reference, where energy becomes E subscript v times the t as measured in our reference frame, plus the the momentum and the x, the position vector, as measured in our reference frame. And now we use Lorentz transformation, and you see we can go from one to the other. We can analyze what's going on and measure these relative quantities in our reference frame and in the reference frame of the electron itself. The important thing, and this is the biggest nonsense combined with the the interpretation of the Breuil's wavelength as some kind of linear wavelength, where you get crazy dispersion relationships, and when you try to solve a wave equation, runaway solutions, infinities, and all that. That all goes away when you interpret the Breuil's wavelength as an orbital frequency or a circumference of motion. And that's also where the other stupidity which I found is that in mathematics, the imaginary unit is the imaginary unit, and sort of a mathematical quantity. In physics, the imaginary unit is basically a rotation operator. And it matters if you go from, let's say, a position that we will describe here by +1 on the x-axis and 0 on the y-axis, and we go to -1. Well, it matters how you get there. And so in physics, that blue arrow where we go from +1 to -1, or from position, let's say, +1, comma 0 to -1, comma 0, where we use 2 coordinates, or we can do it in a 3-dimensional. It matters. You're going to spin from in a clockwise direction or a counterclockwise direction. The blue one is one. That's where you also need the geometry of the electromagnetic force. You know, we're talking about a planar movement here. So are we looking from the front, from the back? But that all gets solved when you analyze the electron as you know, a spinning charge. And it generates a magnetic field that keeps that charge in place. But the point is there that, you know, wave functions, the plus and minus sign, that I followed the course with EDX on quantum mechanics, where they start basically by saying, well, you know, plus or minus 1, you know, that's a convention. Unfortunately, most physicists will use the plus convention. You know, that's nonsense, and that's where quantum physics went wrong. And said, you know, we exclude spin. We are modeling like theoretical spin zero particles, while everybody knows that, yeah, particles have spin, and it's probably their most essential property in terms of explaining, you know, the structure of a hydrogen atom and other atoms, and, you know, ionic bonds between atoms, why hydrogen atoms come in pairs and all these kind of things, because there's spin coupling. There's spin coupling between atoms, there's spin coupling between the electrons in an atom and the protons in the nucleus. There's spin coupling is everywhere, and it explains most of the basic chemical properties, or, you know, I would say most quantum mechanical you know, things that happen at the smallest of scale. So again, there I'm going to refer to my papers, because I see that I'm talking. I really thought I would be talking only 10 minutes, but clock is really ticking. I'm already at half an hour for some reason. But we have that. Fortunately, we are almost there. Then you will have heard a lot about wave equations. What is the, you know, there's Klein-Gordon, and there's the Dirac equation for an electron in free space, and there's Schrodinger's equation. Schrodinger's equation is often presented as being not correct relativistically. It is. Look at my papers. I see basically it's a heuristic argument. It's a bit like Einstein's relativity theory, you know, it's but the framework out of which that Feynman, for instance, uses to derive Schrodinger's equation, he does it in the context of an electron moving through a lattice. That's relativistically correct. There's it's just at some point in time, you know, he struggles with the concept of the effective mass. What is the effective mass? Well, that point-like charge inside of an electron, we could say its kinetic energy is like half the energy of the total electron, so its effective mass, you know, when you do conversions, it's like half the effective mass. It's like half the total mass of the electron. So yeah, the mass of an electron as a whole is 2 times the effective mass of that point-like charge is spinning around, and that's where Feynman and others, you know, go wrong on Schrodinger's analysis, where they, you know, they start mixing that concept of the effective mass of the point-like charge inside of the electron with the total mass, and then there's 1/2 or 2 factors that mess up, and again, you know, when you try to do a dispersion relation or whatever, you get into trouble. This relationship that I'm putting here, you know, the wave function, the first order derivation in regard to time, psi or phi, I think it's psi here, whatever symbol you use for a wave equation. So, you know, wave equation is basically an equation that of which the solutions give you the possible motion in time. So the wave equation is this one. You will have seen that it's Schrodinger's equation without the potential energy term. So we're not analyzing an electron here as part of a hydrogen atom where it's circling around a proton. So we leave out, you know, it's in free space. There's no electric field. There's no magnetic field. So the term is that not there. So you take Schrodinger's equation. You can Google it, and you just put the potential to 0, and then you get this the imaginary unit times h bar divided by m. You will find 2m, but I said there's this mix-up with the effective mass of the point-like charge. This models the movement of the point-like charge, and it's really that very complicated thing that I showed you on the previous slide. You know, that ring current that, becomes like spiral-like. This is what we are modeling, the motion of that point-like charge, not of, well, it's the electron as a whole, but it's basically the motion of that point-like charge. And so the structure of that motion, that gives us the electron as a whole. Times the second order derivative with regard to the position vector of the same wave function. So this wave equation, so we use there the operator that you know when you do second order derivations towards position vectors, you have it's the delta operator squared. This wave equation for an electron in free space, I said, you can go to the paper, and there I write it out. Go to that paper, the Broadly's matter wave constant. It's my most successful paper. It's got almost 15,000 downloads now. I worked that out, and it produces a sensible dispersion relationship. You don't have like wave functions that, indeed dissipate, and because if they dissipate and they're supposed to represent a particle, we know in real life particles don't dissipate. An electron is an electron, and it has its integrity as a matter particle. So you can read more about that. What I just want to note here, and I don't want to show, is that you often hear that the trivial solution for this wave equation is indeed that elementary wave function, which I write down there. Maybe you won't recognize it, but it's Euler's number with an exponent, an imaginary exponent, I as a rotation operator. The plus and minus, is the spin direction of that thing. Times the rest mass, the rest energy, divided by h bar times the t, with the E0 and t, again the energy and the time in the rest frame, the inertial frame, the reference frame of the electron itself. And then we have, of course, an amplitude, as they call it, or the radius, and that's just h divided by mc, but I multiplied by c divided by c, so I get h bar times c, and I get mc square under the dividing line, so that's E. So it's just another way of writing that Euler's number times, to the exponent plus or minus E times the phase of the vector. And instead we can go from the inertial frame of reference of the electron to our moving frame. So that's just a general wave function. I write it below there, but with a few substitutions. And now I just need to prove that it solves that Schrodinger's equation above, because if it does, it's consistent. We have the solution to Schrodinger's wave equation, and it's what is the solution? Well, it's the elementary wave function, which represents indeed the physical motion of that point-like charge inside the electron, and it can take on very weird patterns, as we saw that. This mathematical symbolism is very powerful. So how do I go about it? Well, I write it out. There again, we have the time derivative. We have the second order position derivative times imaginary unit times h bar divided by m. So I worked it out. You can see the second line there is delta, and then between the brackets I write that elementary wave function as a trial solution, but it's of course the solution over delta t times imaginary unit. Again, I do substitution there. I'm not sure why. I add c square, and above the dividing line and under, it's to make my other derivations easier. In regard to the second order derivative of the same wave function behind. And so that looks very formidable, that first equation. So I start working by parts. First the left hand side, and take the left hand side of that second equation. I work it out, and the result is a plus or minus imaginary unit times c times, again, because these are cyclical functions, the elementary wave function, e plus or minus imaginary unit e divided by h bar t. So now I do the right hand side, and that looks a bit more formidable, because we have like time as a variable, and we need to do a second order derivative in regard to the position. So how do we go about that? Well, it's kind of easy, because I said we have this linear motion, and we're gonna write it out as a x. Well, the position vector, it's linear motion combined. We have the motion. It must be the velocity of the point-like charge time, times, and then we choose a suitable starting point for time. So we write that out. made a small mistake. Should be x minus c time or x c times time. So again, that has to do with the spin direction, and it depends on your convention. For if it spins in this direction, we call it c times t, or if it spins in the other direction, we call it minus c of t. That's again where I'm flabbergasted by the ease with which quantum physicists are like, well, it doesn't matter, it's convention. Well, no, you're modeling something real, and so you need to think about directions in space. But in any case, to make a long story short, we can substitute t for x divided by c, depending on your convention, whether spin goes here or spin goes there. Otherwise, it's minus x divided by c. And if you write that all out, the right hand side of that second equation using this substitution, then you get exactly the same value, the same function, sorry, plus or minus imaginary unit times c times the elementary wave function. So the two sides of the equations are the same, and that's it. Bingo, that's okay. It works. So that's really all that there is to it. We have the electron model, the proton model. For the proton, there we're working with a three-dimensional oscillation, so we would have to work out like an elementary wave equation like Schrodingers for the motion of a proton in space, and I'm sure that's a bigger headache than working out Schrodinger's equation. What we do in the paper is, indeed explain it, how Schrodinger's equation works in the context of a hydrogen atom, and when there's also not only electrical fields but magnetic fields. But I refer to the paper. That whole exercise should be done for a proton, taking into account we have an oscillation in 3 dimensions. But that's because people didn't think about a proton model basically, and assumed this infinitesimally small positive charge is the proton. While I'm thinking like, no, a proton has mass, a rest mass, because basically it's a charged oscillation, and so you need to model that and you need to see its structuring. So what we're doing here, we should do that for the proton, but we're not going to do that. That's maybe a retirement project, or others will pick up upon these ideas and win a Nobel Prize for that. I hope. Good luck. So that's where we are, and where I should probably conclude. Here I will show, I think from all the stuff I wrote, these are the most important references. So the guys who, or the ladies and men amongst you, who are really interested in more the speculation that I said, like dark matter in the universe could be explained when we assume our left-handed electromagnetic force, the force we see in this world, which explains matter and antimatter. There's a mathematical possibility that we could have a right-handed force, and that might reign over some other parts of the universe. And that would explain all of dark matter with about 80%, according to gravitational models. The second reference is indeed what I've told you on the proton radius. This derivation, it's actually a complicated derivation, because I actually started not with these easy mass energy equivalence relation and then this modified Planck-Einstein relationship. No, I really took the measurable properties of a proton, its magnetic moment, G factors and that kind of stuff, to get that theoretical result, which matches experimental results on the proton radius, 4 times h bar divided by mc. Pair production, I said that's a big mystery a little bit, because I said charge is charge. You can't reduce it any further, but what we do see is that this Perantipair creation in nature from cosmic rays as they enter the universe. I suspect that charge actually doesn't get produced out of nothing or annihilates into nothing. The energy gets conserved. The gamma rays that come out of Perantipair annihilation, they have a huge energy, and that energy matches the energy, the equivalent of in energy terms of the mass that got annihilated when a proton and an antiproton annihilate each other. So, but I suspect a lot of these reactions, the experiments, they take place near nuclei. So maybe the neutron participates, and there's other stuff going on. There are experiments outside of nuclear, but then we have like an electron beam, and maybe there's maybe there's stuff going on, funny accounting and whatever. I speculate about that because that's sort of the I would say the only mystery where I wonder like how does that work exactly. So, but I have a few hypotheses on that. On pair production as a nuclear process, as I call it. It's actually, to my surprise, but it shows that other people are struggling with that too, and are finding my idea sympathetic. It's the second most downloaded paper on ResearchGate among my list. And then I said the Broglie's matter wave, the concept issues. I cannot believe that Einstein didn't see what I and others see. I mean, there's a lot of people working on electron and proton models in the last decade. I'm not the only one who sort of thinks like, you know, the electron and proton must be something like, you know, oscillating charge. The Zitterbewegung, it's a concept that was revived by David Hestenes, who is a mainstream physicist. You know, he revived it in the 1980s and 1990s, but I was in touch with him also. He says, yeah, there's little appetite, you know, people keep the mystery alive. I don't know why, maybe for funding, or maybe because, you know, the whole thing's nuclear must remain a secret. I don't know. Any case, that's a paper worth to read. I've revised it several times. I think it's a nice one. The Planck-Einstein relationship, that's the other paper, lectures on physics. You know, I have like, you know, some of my lectures, it's a bit of a joke. Feynman had his lectures on physics in 3 volumes, you know, classical Newtonian physics, and then electromagnetic theory, and then quantum physics. So I analyzed those. These are actually basically the basic textbooks I studied. And, you know, there's a lot of stuff I think like, you know, why didn't you model this correctly, or mistakes? So I rewrote, rather jokingly, a few of his lectures. And this is one which I find interesting. Why it explains basically the Planck-Einstein relationship, how nature is quantized really. Why can't we observe, you know, sub-Planck level variations in fields, as I call it. You know, if the electron is actually nothing but, you know, a spinning charge, you know, we must have some very, very small variations of the electromagnetic field, right? Well, according to Maxwell's equations, yes, but in reality, no, because Maxwell's equations, they're valid for charge densities. You know, when you go to the really small scale, the concept of density doesn't make sense anymore, because the charge is either here or it's there, but there's nothing like a density. You know, half of the charge is here, or, you know, no, the charge is either here or it's there. It's not sort of smeared out. So talking of charge densities at the smallest of scales doesn't make sense. And that's what I explain in this paper, where you have indeed, you know, and that's probably, you know, there's a lot of talk about complementarity in physics, but that's the complementary viewpoints you need to have. At the smallest of scales is the Planck-Einstein relation, and, you know, it's this point-like charge, and yeah, Maxwell's equation in terms of the magnetic field that it generates, they apply, but the field is quantized. And nothing can happen to this system, this perpetual model. You know, it doesn't radiate energy away. There are no field oscillations. It's only when you know, it gets in an excited state, and these excited states will be separated. These two states will be separated by Planck's quantum of action, which Planck's quantum of action, physical action. It's a concept. You know, it's the product of time over a distance, and you know, it's and energy. You know, it's energy times time, or momentum times it's energy over a distance, or momentum over during some time. So you can write it in various ways, and that's how it translates into, you know, at some point in time, a photon that gets exchanged between, you know, particle or a particle system and the field. But that comes in chunks of energy and momentum that are defined, you know, by the Planck-Einstein relationship. So I explained that there. It's related to that chapter 3, the concept of a field. I told you, like, you know, we can analyze photons also. Photons are like, you know, yeah, they're traveling fields, disturbances of a field, and they really are point-like. Probably not infinitely small again, because we do have like photon collisions, but they're extremely small. They're probably at the smallest scale that we actually can imagine, much smaller than proton or electron radii. Then the other papers are basically probably some concepts that also are related that you need to read maybe to understand the other papers. I have a very basic one, that's the one at the bottom, Lectures on Physics, Chapter 1, Quantum Behavior, where I talk about the basic questions that usually physicists start with. You know, how do we explain like one photon interfering with itself in the Mach-Zehnder experiment? I argued there that you know, a photon actually, if it's circularly polarized, it means that its spin is composed of two linear oscillations again, and so you can have two linearly polarized photons coming out of one when you send it through a polarizer and all that. So there's a lot of hanky-panking going on in these experiments where, you know, a photon is not just a photon, it has structure again. And, you know, it matters a lot of whether the photon is linearly polarized or circularly polarized. So if you're working with circularly polarized, you can imagine just like you can split a beam, a photon beam, circularly polarized beam into two linearly polarized photon beams. Well, we can do that at the level of a photon as well. And I talk about electron interference. You can imagine if we have this complicated structure, well, complicated, this ring current, point-like charge sitting around, and you force a lot of these electrons, these structures through a split. You know, it's going to interact with the material. It might sail through, but you know, because it's charged, it will interact with the, you know, it's like a cage of Faraday or whatever. It will bounce back or it will get through, but you will have this interaction, and that explains, because of the wave-like nature, so it's an orbital wave, not a linear wave, but yeah, it's normal that we get like a wave-like interference pattern, even if it's only one electron, because you know, you don't know the initial conditions of the system, when it arrives, where exactly it arrives. You know, there's a variation. An electron beam isn't like you know, it's the electrons are fired over when they go through the split, over the range of that split, the width of that split, and so yeah, how they interact with the material of the split, you can see it. And I show that actually because this is interesting. It's something that I noted in Feynman's lecture also. He gives this prediction of like a wave-like interference pattern of the electron. When you really look at the experiment, the way it was done, that Feynman said it should be done, that was only in 2012 that it was done by Batelan, University of Nebraska. They produced these very detailed pictures with nanometer technology. And it shows a very classical, we call it in photography an airy style pattern, where there's no sharp lines between, you know, the areas where there are little electrons arriving and the areas where there's a lot of electrons arriving. You know, it's yeah, there's clear separation between these zones, but not a clear separation in terms of one line. No, they are spread out a little bit, and so it's what you would expect when you have just a normal wave. A water wave or any wave that is composed of like water or water molecules. You know, yeah, the micro pattern that you see arriving, it corresponds to the pattern that you see from that real life experiment, which I think is one of the most defining experiments that was made about 10, 11 years ago. And deserves a Nobel Prize, I think. I'm saying that aloud here. I'm really surprised Batelan and his team didn't get a Nobel Prize. They should, because it shows that quantum mechanics can be understood, and it can be understood in a pretty, what I call, you know, a realist way of looking at how electrodynamics work when you go to the smallest of scales, and when you're thinking of particles not as zero dimension things that have no properties whatsoever. We know they have properties, a magnetic moment, a g-factor, angular momentum. So when you think about that structure and you have a model for that structure, well, all these things start making sense. And that's why I called my my presentation here the end of physics. We know it all. I am convinced that physics is not interesting anymore because there's nothing to discover. What is left, though, is a lot of engineering and working out the consequences of these, you know, things I just presented now. and I hope that will inspire you, because Feynman, as you know, in the 60s there was really like no one was interested in elementary physics anymore, and he tried to sort of draw you know, the brightest of the brightest to physics again, to feed them into the industry or the military industrial complex, or I don't know what, but he really tried at Caltech with these lectures to raise the interest of young bright people, and he failed, and I understand why he failed, because, you know, he couches his thing like, well, you know, we're never gonna quite know how things work. We can, and it's fascinating enough. And this is the main thing in my life, and my interest in these things is, you know, at some point in time, you do arrive at a point where you say like, wow, I understand how reality, what it really is. I also understand at the same time, the magic of it is that I can never know the initial state of these things that happen at the smallest scale. So I can only do predictions in terms of you know, statistics. So we have a statistically determinist worldview where causality plays, and at the same time, yeah, we can't predict the end state. And then you have this wonderful world of you know, atoms and molecules, and then, you know, how anorganic molecules are formed, and they come together then in sort of a cell-like structure and leads to life. You know, the more you know, and the more you realize that, whoa, it's the end of science, the more you also have sort of deep respect for what we do know, and where you wonder, and where you do see like, you know, this is great. It's great to be alive and to understand these things. And at the same time, as a way of conclusion, for older people like me, I've served as a diplomat. It's also sad to see that, you know, that wisdom, that science, it doesn't translate into a more just society. Europe is at war again. You know, the cycle of history and bad things, and, you know, super ambitious politicians who sort of don't care about you know, going to war and the people it kills. You know, that's a sad thing to see, that the rationality in our societies is unfortunately not as advanced as the field of physics or mathematics. So I know I sound a bit emotional in that thing, and this is not good, because I work as a professional in the ICT sector. This hobby already, you know, my family, friends, and some of my colleagues say like, you are a bit nuts, aren't you? So it's not good for my reputation. At the same time, you know, one has to have fun in life, and one has to talk about what he believes is true. And this is an area where, you know, it's much more, it's much less stressful, I would say, than thinking about how our world operates and politics. So I'm happy to talk about these things. It calms me down, and I hope it helps you to sort of, you know, go out, look at these things, and have an interesting conversation with yourself or with others on, wow, how does things work at the smallest of scales, and what are kind of the implications indeed on you know, our theories on cosmology, the universe, and how we fit in. And you will see it makes you feel lonely at times, not because you don't have any friends to talk about this, I do, but sort of like, wow, we are this mind developing in a physical body, in a biological system, and we're making a mess with climate change. I mean, we're growing so much. We're not running against resource constraints. It's just like, you know, pollution, greenhouse gases. We're changing the biological system. That's the Gaia hypothesis, but it's science. We live in a system with a certain thermal equilibrium, and for the moment, these greenhouse gas emissions, they make it hotter, because we have created a system, an atmosphere that absorbs more radiation than it emits. I mean, the balance has changed. It's always been like that. You know, thermal system absorbs radiation and emits it, and the balance between the two is always there, but it determines how hot the system becomes, and our system, the Earth, is becoming hotter with 1 or 2 degrees. It's significant. So yeah, we are changing through the fact that we are here, a dangerous situation for our own life. And at the same time, science, mankind has never been where it is now, where we do know everything and have technological solutions for hunger already since a long time, for energy, for so many things, and yet we don't manage to apply them and live in peace with, between different systems. Again, I've talked for 1 hour. It's my last lecture. I hope I don't sound too crazy. And if I do, then probably you're not watching anymore, so I don't care. Have a great day and have a great weekend.